So let's continue with our root finding. So the main take-home point is that root finding or finding a method that is foolproof and always works is difficult. Ain't gonna happen. Okay? So we have first class of the methods that we looked at were methods that start with the bracket or the interval, okay, where I know I have a root. And the intervals of that sort we already identified as like, okay, at the end of the interval, if I evaluate the function, it should be positive at one end, negative at the other, which we test by checking the multiplication of the two. And if that multiplication is negative, that is our test that we have a bracket. And then we just somehow find a way to make this interval smaller and smaller and smaller and sort of zoom in into that root. And what I need in the process is, well, when is it okay to stop? Okay? And then we stop. And that's the end of it. So any kind of numerical method actually works this way. It has some algorithms that is proven to work in certain cases. And you need a starting point and a stopping criterion for that algorithm. And then you are close to your solution. Okay? And you're not precisely at the solution for two reasons. Okay? One is the fact that you stopped at some point and you can't just go infinitely, so that some sort of a truncation is happening. Okay? So you know that even if you have like any mathematical formula that is solving for anything, I gotta chop it off somewhere. I can't go and add infinite number of elements to my summation. So there is some truncation going on, so I gotta stop the algorithm at some point. And also I don't have correct representation of numbers of computers, which is fine as long as it's limited, as long as it doesn't pile up. Okay? And some methods are worse than the others in that regard. So there's always some sources of error. It's never perfect, but it's good enough. Okay? Our bridges still stand, our buildings are still there for a while, right? So obviously we're getting something right when we actually go plan, model, and execute some engineering problem. So, without further ado, with root finding it might be difficult, but we will learn 5 or 6 methods or so. Okay, and part of our testing will be okay. Can you evaluate how is this method doing for a typical problem? Okay. And also, can you just implement the method? So to a certain extent, let's look at the Newton method that I presented at the end of the last class. So Newton method is one of the methods that simply starts from a point and then iterates and hopefully gets better and better in that iteration. So if I told you nothing about how we came up with this method, that method has a formula. And that formula will show up in the screen any moment. Oh, okay. And then I'll have to go and switch displays. Okay? So that method has a formula which says xi plus 1 is xi minus f of xi divided by f prime of xi. So I know that I'm looking for the root of function f, so I'm looking for some x such that f of x is equal to 0. Okay, that's the root. And even if I didn't tell you anything about how this came about, okay, can you program this? Okay, so I can spit at this point any formula, just give it to you and say, hey, this is an algorithm for root finding. And you should be able to tell me that that really is the case. Okay? So, first thing you should be able to implement it. So I need a loop. Okay, that loop will have a starting point. Let's call that starting point x0 or x1 or whatever you want to call it. Okay. X old, sometimes in programming you call it x old. And then my new iteration based on the old iteration says that I should for x1, according to this formula, x1 is x0 minus f of x0 divided by f prime of x0. x2 is x1 minus f of x1 divided by f prime of x1. x3 is x2 minus f of x2 divided by f prime of x2. And I keep going. Okay? When do I stop? And at each point, I will evaluate the error between the last two iterations. So at iteration 3, I'm going to look at the relative error between x2 and x3. At iteration 4, I'm going to look at the relative error between x3 and x4. At x5, you get the point. Okay? So every time I have this old iteration and this new iteration within the loop, and I'm going to look at the relative error between the two. And I'm going to stop when I find that relative error small enough. Now, we could write a philosophy paper on whether I should use absolute error or relative error. Okay? Either way, you're eventually going to get close enough. Okay? The reason to favor relative errors is then when if you're trying to generalize a method, okay, and then you're not so dependent on the values of f so much. You kind of normalize by the value of the root itself. Okay? So it's relative to the whatever root. So it's your error is then 10% or 0.1% or 0.01% of that root, whatever that root or close to that root might be. Okay? So you're a little more general, if you will. Whereas in absolute value, it's just the absolute value between two sets. Okay? That's philosophically why I personally prefer relative error. But ultimately, if you are converging, you're just going to get closer. It's going to be at some point good enough. And this error evaluation and when do you stop is sort of just a relative measure. But hopefully you're actually just converging and getting close. And to a certain extent, how close you are doesn't matter all that much. So you have to get comfortable with the fact that we're never exact. Okay, we're always close to a root. And we can control how close we get. And that's about it. And in root finding, I'm happy that I'm actually getting close. So let's, just before we actually get back to programming this, again, to a certain level, if I give you a function, you should be able to plot the function, try it out, and see how well it does, regardless of the method that I give you. Okay? You should be able to evaluate that. Now, what's in Newton method and why it's actually fast, what it does is says, okay, I'm at this old iteration xi, and my next iteration I get by approximating my method with a straight line and just shooting it down to 0, saying, okay, that's going to be my next iteration. Okay. And based on f prime, which is the slope of this, that's how I get that formula right there. Okay. There's actually, there's also a way to find this formula from Taylor's formula, believe it or not. Okay. It's proof in 2 lines. It's not difficult, but either way, it's an algorithm that this is what it's doing as a guiding. Okay. But then I still need to try it out to see if it works. So it works. Obviously, this is the root, and this is how close I am to that root. Okay. A lot of methods will get me to the root when I'm this close. But there are certain problematic cases where it doesn't work. And here are some of them. Okay? So one problem might be is that I'm near a point where my f prime is 0. And I'm dividing by f prime. In that case, I'm going to get gross errors and I'm not going to converge with Newton. So in 2 cases, one is actually inflection point, okay, where function is changing from basically having a positive f prime to negative primes. That can be a common problem for having with this method. So not only f prime is 0, but also f double prime. So here's x0, okay? So here, if I'm looking at the f prime, it's going to send me down to this point. This is my next iteration for Newton method. Okay? And then at this point, if I look at the f prime, it's going to send me over here because this is the derivative and where it intersects y is equal to 0. So then I'm here, and then I'm going to get at a milder slope, and this milder slope is going to take me outside of this plotting range for x3. And then for x3, I'm going to get into a milder slope close to 0 that is going to send me even further away on the other side. So I'm going to keep bouncing back and forth and further away from my actual root. Okay? And I'm not going to converge. I'm not going to find the root. And root is sitting right here. My mouse, for some reason, is not very responsive. Right here, smiling at me. Now, if I actually started closer to this point where I wasn't, that could have been prevented, and I could have slid right down to that root very quickly. So where I start my iteration does matter for Newton's method. Here's another problem, and this is the one around the valley here. So I'm trying to find the root, and root is right here. Okay? And let's say that I start around here somewhere. Around here, somewhere, it's close to f prime being a 0 because I have a local minimum, right? Remember your calculus class and local minima? So this local minimum will help me just simmer in this bowl, okay? And never get over this mountaintop right here. Quite literally. Because if I pick any value here and start from it, I'm going to constantly send, you can actually, so let's say that I'm starting at x0, which is here, okay? The tangent will send me down to x2, x1, which is here, okay? And then this tangent will send me down to x2, which is here, then x3, x4. I'm going to kind of come around here. And then around here somewhere, I'm going to divide with f prime, which would be very close to 0. So I'm going to get some huge number. And I'm just going to go to infinity. Okay? So I have trouble getting over that mountaintop. Whereas if I was starting my iteration from here somewhere, no problem. I will find this root in no time.
Are you talking about the second image?
Yes. So you're not seeing it at all? There we go. See now?
Yes.
Okay. So basically, this is, yes, so I'm talking about if my starting point is near this minimum, okay, the method will just keep sending me around here, but eventually I will get very close to f prime being 0 at this point, right? And when I divide by that, I'm going to get some huge number, which will cause an overflow, okay? So I'm not going to find, and what I'm finding is this root. So I was talking to myself this entire time and you didn't see the mouse. Great, because I can see it on the screen. So here is the root that I'm looking for. So basically, I cannot get over this. Look at this. It's not sensitive enough. There we go. I cannot get over this mountain here. So, but if I start on this side, okay, I'm going to kind of slide down this tangent in no time. So I'm going to iterate it like 2 or 3 times and I'll be done. So I'm very sensitive to where I start. And sometimes you just have to kind of try out multiple points to start. Now, there could be more different points. So basically, the best remedy is to kind of guess sufficiently close to the root. And for some functions, they can be very difficult, in part because I might have multiple roots at the same point and multiple derivatives 0 at the same point. So if I have actually a function that is sitting on a 0, like x squared, right, I have a double derivative that is 0 there as well as derivative, and that can cause trouble with these methods. So you have to live with some of that. Okay? Now for polynomials, we actually have more effective methods for polynomials that we are not going to go into details, but there is software that just handles just polynomials, and that can be helpful. Okay. Now, there's another.
What do you do if you have that first example?
In this first example, again, you have to be close to the root. So closer to the root is better. And bracketing method will work here as a more of a brute force, but you have to find the bracket. So one part or one way to go about this is that when you have a function, you first actually sample your domain, and you look at all of the subintervals, and you look for the bracket. So sometimes you also want to look for all of the roots, in which case you have to scout the domain, and every time you find the bracket, you go and find the root, and then you move on, right? So sometimes you have to have this smart search over the domain. And there could be intricate problems with very nonlinear functions, and especially with functions that change rapidly for some reason or the other. Because then you might not have enough sort of resolution to get zoom in. Okay, so you might skip certain roots. But that's just, now in practical applications, you will be, so for instance, tasked, you will have an engineering problem, just give me one moment. You'll have an engineering problem, and that engineering problem is probably something that is repetitively happening at the site you're working on. Okay? And let's say that engine is something to do with like rheology. Often we have to actually find the roots for that. So you're going to have certain cement slurries that you're working with, and they're going to have rheology in certain range, and viscosity is in certain range. So you're going to test your method for certain type of functions. And you're going to test and find what works on some example problem, and then you're going to be running it from there on for the next 3 months. So in that sense, this procedure will be good enough because you're going to test it. You're going to have a test problem, and all of the others that are coming along will be relatively similar to what you tested it for. Okay? So it's going to work for some time until it breaks, and then you've got to adjust. But that's why they're employing you with your higher degree, so that you can, next time it breaks, you come in and fix it, and you keep going, always understanding. And also they employ you because you're going to, based on these simulations, you're going to try to find better rheology that works better for the system, so you can optimize it. Okay? So that kind of mindset. So these are just tools that are going to help you along the way, but your job is design, your job is improving the problem that you have right on site. And that is something that is a moving target. Okay? The technologies that we have right now are not the technologies we're going to have 10 years from now. There's no way to know what you're going to deal with 10 years or 20 years from now. Just look at the computers and your phones, how they look like now versus how they look 5 years ago. Okay? So you can get the idea. And I don't know that. Well, how many of you have had the phone where you have to... She's laughing. Yeah. There's 2 or 3 of us. But most of you have not... You know that the quintessential picture of a phone is that phone handle that nobody sees anymore. Okay?
I got my butt busted with phone cord. Y'all don't know anything about that.
Right. So I had to... And I still know 3 or 4 numbers. Phone numbers of my closest friends in high school because I knew it. 3 or 4 closest friends. I barely know my husband's phone number right now, right? Because it's programmed. let alone my close friends. I really know 2 or 3 phone numbers. The rest, I'm just counting and pressing the button and going. But then you have to painfully turn your phone to actually get the call. Then you can imagine the rest, okay? I have mechanical memory of the phones of my best friends in high school. I kid you not, I could rattle them off right now. All right. Now, sometimes, so Newton method, when it works and when I'm close enough, it's fast, okay? Now, there's one method which, so I'm sometimes troubled with f prime. If f is actual function that I have, as a formula, I can evaluate f prime, no problem. That's what we went to calculus for. However, sometimes I just have data. Okay? My function is actual data. Okay? And then my f prime has to be approximated. Or sometimes I just don't want to deal with a complex function, or I want this to work a little more general. In which case, I can simply approximate f prime, or 1 over f prime, with this finite difference. Do we recognize the slope in here? So my approximation to f prime is f of xi minus 1 minus f of xi divided by f of xi minus 1, right? Values of the function divided by the actual distance. And this is just 1 over that, 1 over f prime. Do we see that? Okay. So if I approximated my f prime with a slope between 2 points, the last 2 points I dealt with, okay, so this is just linearization, then I can just have this formula, and we call this secant method. And the only difference is that I actually now deal with 2 previous iterations, not just 1. And I have to program accordingly. But other than that, if I give you this formula, you should be able to set up a while loop that starts from some x, and given f, can figure it out. Okay? Even if you knew nothing about secant method. So with that, we're just actually going to now deal with a couple more. So you can work with, this is the function we worked with last time with. We can either work with that, we programmed fixed point iteration for it in Newton-Raphson, but I don't think we had the time to see how Newton-Raphson is doing, so we're going to do that now. And then you can actually program any of these methods for any function f. And the only thing that you change is how you evaluate the function, okay? And you're going to get a lot of homework practice for that. And I now realize I forgot your question. Somebody here was asking a question, yeah. But you possibly forgot that question too. No, you didn't. Good.
So for the Newton-Raphson, what's basically the only real advantage is speed?
Speed, yes. So, and only real advantage is relevant. So let's say that you're cutting down the steps to find the solution from 20 to 10. You're chopping them by half. Okay? If initially to process however many points on your well log took you 1 hour and suddenly it's half an hour, that's sizable enough. If it's a day and half a day, okay. So if it's just 2 minutes, you don't care. You go grab a cup of coffee and by the time you're back, your solution is on your desk. But when certain things run repetitively for a million cases, that's where the problem is, and that's where it piles up. So for individual case of finding a root is not an issue, but everything you're kind of interested in. So let's say that in common problems where we have to evaluate is flash calculations in thermodynamics. And when you're running them in a reservoir model, for every reservoir model box, you got to rerun something. What is my pressure here? What is my temperature here, right? So you got to reevaluate your equation of state. And if you're running root finding for every cell, for 2 million cells in your reservoir model, you get the picture. Okay. So cutting down something from 20, now again, in all of the examples that we're running here, it's going to look trivial. Oh, what? So it's 20 steps versus 10 steps. By the time it prints it out on your computer, you don't even notice the difference in time because it's less than milliseconds. And we can't notice the difference between something that is less than blinking. You can measure the CPU time, and there's a way to measure, so you can actually see how fast something went. But again, when you have to repetitively update at 2 million points and multiple, that's just in space, but you also have in time. Things are progressing in time, so at every time point you have 2 million points to evaluate for. Get the picture. Okay? It's long, so anything cutting down by any amount is good. Right. Because if it's too expensive, then it becomes again evaluation of a reservoir with all of the petrophysical evaluation, running the samples and all that, the initial well logging. That can take 2 to 3 months. So if you're one portion of it, you cut down from 1 week down to a day. That's great. Because there's time is money. All right, so let's pick any problem. We can do Peng-Robinson root finding. We could pick anything. I'm just going to quickly look at what we did last time. So we did Newton's method iteration, okay? So I set up my maximum number of iterations. I set up my starting point as 0. This epsilon, again, there's a little bit of leverage that you have here. It's some small number. Initially, you initialize error as 1, iteration as 0, and this I actually don't need to initialize. And last time I called this f of x and df of x, I realized that up there in the code I already have f of x, so I don't want to clash with that, so I just called it ff. You can call it f1, just call it something different, so you don't clash with the previous definition of f. Because typically when you have two same definitions of function, the code will go for the first one. And that can introduce a little error. So this is in the class of avoidable errors. Right? So I'm just renaming it ff. And then, so this is my f is, again, we're looking for the root of x to the 4 minus 6 minus 10. And then I'm defining evaluation of this function f as well as derivative. And then I'm going to say, please iterate in a while loop while my error is larger than some epsilon and my iteration number is less than the maximum that I allow. And again, my Newton, if I just gave you the formula, I initialized things as x0, that's my old iteration. And my new iteration is xi plus 1. This is what it is as a formula of xi and my function f. So basically, I literally write down it's x0 minus evaluating a function at x0 divided by evaluating the derivative. So that's my next iteration. So in terms of implementing these in any root finding or in any algorithm, okay, you're given in these iterative methods, you're given what is your next iteration based on the old iteration, or possibly two old iterations. Okay? But the logic is the same. I'm given what is my next step based on what I have right now. And that next step is supposed to get me closer. And most of the time it does. So then you evaluate your error between your new iteration and old iteration. So this is error, evaluate relative error between new and old iteration. And once I have that, I replace my old iteration in new. So the next time I step into this loop, I move on. Okay? If I don't do that, I'm just going to stand in place and keep evaluating the same number. And that's a great recipe for infinite loop. Okay? Your error will not change. It will keep there in its place. Which is where this maximum number of iterations will catch that. Okay? And I just have to, printing is optional, right? And I just have to increase number of iterations. I could have done this at the beginning of the loop, at the end of the loop, it doesn't really matter. And that's it. So this is your shell for most of the root finding methods. Not for most, for all of them. So basically you have to initialize. I'm going to call this initialization. All the parameters, because if you don't initialize them, you won't be able to get into the loop. So let's see how this method iterates. So it kind of zooms in on the value of approximately minus 1.69. And actually, I asked myself just before this class, well, let me just check, how do I visually check that this is correct? I could evaluate f of, let's see, how close am I to 0? So I can say f of, or no, I called it ff. Ff of this is 2 times 10 to the minus 10. That's small. And I can also plot the function. So if I import my plotting tools, I give myself some space of x's. Since it's giving me minus 1.7, well, maybe I need to go with the x's a little more. How about that? Minus 3, 3. And plot x and ff of x, and then zeros. Finding this root. But I do have 2 of them. I have one that is approximately symmetrical. So I started from 0, and because of the shape or the tilt of the graph, I kind of went to this side. Let's try to just change this input value of x0. So this is my starting point. So let's change the starting point to 1. Maybe I'll go to the other side. Let's see. Okay, yeah. So 1.85 is this one over here. I see some, so what are the questions up there?
Can you go back to what you're plotting?
What I'm plotting? I'm plotting, I gave myself x's and then I'm plotting x versus f of x.
And you're plotting it against just a 0?
And I'm giving myself zeros just to see where it intersects. So you do that, you plot x and np zeros of the same shape, and that's going to give you a line of zeros. That's just a hack. Okay, so this is the 2 points. This or the actual?
Yeah, all of that.
All of that. So I import numpy as np. I initialize. Okay. I define my function and my derivative. So this is function. I will post this after the class. Okay. And then while my error is larger than epsilon and iteration is less than maximum iteration, do this. In the remaining time, so what I did now is, like, even if I just gave you this code, you gotta see, like, how is it doing. So you plot the function, you see how it's doing, okay? So even if I just gave you any blah algorithm, please implement it. Okay? You can do so, and then you go and you plot and evaluate how it's doing. Now, let's try this secant method. So does everybody have this code? Or are you just looking at and nodding?
Can you scroll down to the graph part?
To the graph part? So it's just graphing the function. So I have the function defined up there. So I'm really just plotting x and f of x. So I gotta give myself x's, right? And you know, where you limit yourself on the graph limits your view. So if I just did 0 to 3, I would say, oh, there's only one root. Well, I didn't plot anything negative, right? So you do have to play with that a little. Now this is x to the 4 minus x minus 10. Do I have any more roots that I possibly don't see here? Real roots. This is now invoking your calculus class. No, why? For large x, this function is dominated by x to the 4, correct? Okay. So for large x to the 4 is dominant term, and it's just going to run away. And for large x, it's going to be super large. So larger than 3, I'm just going to go larger. I'm not going to hit 0 anytime soon. For small x, same thing, just on the, it's x to the 4 will be a positive version of it. Okay. So for all intents purposes, as I have absolute value of x very large, my function is behaving as x to the 4. And in either way, I'm just getting super large. I'm not getting close to 0 anytime soon. So these are the only two roots. So do you see what I did that? Did here? Numerical part can be very useful. It plots the function in no time. But for a numerical plot, you have to give it where to plot. And if you don't give it the range, you're not going to see. You're going to be limited to what you're asking for to plot. In numerical methods, you're limited to what you're asking to do. And this is where the analytical part, which comes from your calculus class, is helpful to just look at this function. Hey, for large x, it actually behaves as x to the 4. I'm good. I'm not searching for roots there. Yeah? So life is a combination of all the little pieces that you're learning here. So these are the only two roots for this one. I'm good. Okay? Okay. So in the remainder of the class, please take this code and copy it over in a different cell, if you will, and just do a secant method out of it. Okay. So secant method basically it does away with the derivative. It doesn't do derivative. But I need 2 points to work with. Okay? 2 old guesses. So based on the 2 old guesses, I need to initialize with 2 points as well. And this is the formula for secant method. Again, 1 over f prime is approximated with xi minus 1 minus xi divided by f of xi minus 1 minus f of xi. Okay?
You put that in the model, that equation?
Yep. Yep. So this is your next iteration based on the previous 2. So you have to initialize with 2 values at the beginning, 0 and something else. Okay? And then from those 2 values, you get the next one too. And then you have to shift those 2 values by 1. Okay? And move on.
How do we choose the other value?
Choose it. At the beginning, you just choose. Okay? You can let this method evaluate the first one for you, the second one for you, if you will. Do it with Newton method or some other method. Doesn't matter, just choose it. And you've guessed that this is going to be the code you submit online. So the more of it you complete here. So do you want to see while loop or initialization? Here's the while loop. All of it. And this highlighted part is essentially what you're replacing and doing away with. Let me put this. And Ningyu and I will walk around and help out. And I'm going to put the method right here. So I think both of these now are give or take visible. This works? Yeah, if you have the code already, copy it into the next cell and modify. And if not, we'll start all over.
So just substitute.
You have these slides, if you need them, you can download them. But right now I'm just gonna try to zoom in a little more. Better? Last row sees better?
What were you wanting us to do?
I want you to,
I just copied.
modify this.
Modify that.
Or rather, implement this method. It's called secant method. So my next iteration uses two previous guesses. So I gotta start with two, not start with just one. And this is how it gets my next guess. So instead of xi minus f of xi divided by f prime of xi, I'm just gonna program this. So that's changing one line of that code.
Okay.
And adding one more guess at the beginning to start with.
Okay.
And then changing the way you change. So 3 lines of the code are changing. You and now I want to change this line. Remove the end of the part.
No, actually, here on my headphone. I'm sorry.
So now instead of that, we have slightly so we have 2 values, right? So x0 is something else. Something like that. You can call them x0, x1, x2 and change this. I'll leave that to you.
Yeah, I think that's because that's why we have to, in order to compile. Just wait for
So we just did the Newton method, and then we changed it, this is the secant method.
So the difference between the secant method is whether we know what is this tangent. If we don't know the tangent, we use the secant to replace that approximation
Like, it's a really difficult thing. It's not just
Sometimes it's numerical. We have the row of numbers, and we don't know what it is.
Yeah, it's just choose
I mean, that's why there is no derivative defined. There is no definition of a derivative when you have a series of numbers.
Right, but on this one, it's like that we're gonna do, we know that, well, I mean, we define it. Well, they're hard to find. Yeah.
Well, all of the methods you have to
None of those.
use to create the derivative for yourself.
So we just, don't we have to say print to X2? Don't have to on this one, don't have to change.
So about printing is only about seeing or viewing it with your own eyeball. So purely printing does nothing to the program. So you can randomly add or remove print as long as it is defined or modified by
So
the.
we can just really this.
You can print it anywhere you want.
But if we wanted to know the differences, like, because we don't have to replace it. That is to that.
So you have to add everything at one to everything here. So this becomes x2 minus x1 equals now x2 is your value.
So we have to put it here. X2 minus x1.
X2.
And what about
And so x1 equals to x2. Okay. Before you do this, do x0 equals to x1 before you say. Now you have to update two values.
So we just had it on the top.
Yes.
I think I did this last time. I couldn't get my maybe because instead of x1, I was hitting x and L.
Maybe.
It's supposed to be a 1. It's supposed to be a 1.
It's very probable.
Because I kept thinking x1,
Yeah,
x1.
that's this much apart. Because one thing's one said one and the other.
So you need some better.
So it's my.
Yeah.
Do we have to plot it?
Google those.
Where's starting point?
Doesn't know.
Yeah, where's, oh, so you didn't do starting point, so you need 2 x1. So I have to
Yeah,
get
and
0.
by the way, there are
It's different font to do it in.
yes, there are several hundred of this kind of fonts.
Oh, to make it
There
more
are
clear.
several very popular ones, and some of them are free. You can find them online and choose the one you like best. So some of them they do one like this,
Yeah.
L like